What I wanted to do today, well, actually, let's let this ride. So we'll start off with our normal dialogue today. We made the point last time that we talk about contaminant hydrology, and on top of groundwater hydrology, physical hydrology, if you like, there are two things that are of interest to us. And that is that if we're dealing with these so-called non-aqueous phase fluids, then what we might be interested to know is something about how they behave in the subsurface. And we can divide that conveniently into two steps. One is how they migrate as individual non-aqueous immiscible fluids. And so here is kind of a cartoon in some respects of spilling denser than water fluid in the subsurface that hits the blue groundwater table. It's in German, of course. I just found this online 2 seconds before I came over here. And this immiscible fluid, because it's denser than water, in the same way that if you drop a ball bearing or a marble in a swimming pool, it goes to the bottom because it's negatively buoyant. And the fact that it has to go through a porous medium and happens to be a separate fluid, actually the physics are not very, very different from those two circumstances. And so what we'd like to be able to understand a little bit about, since non-aqueous phase liquids are perhaps the most difficult liquids to understand rather than dissolved fluids, is one, what it does as it transits across the vadose zone. This zone here, which is partly filled with water. The water table, if it's denser than water, we'd expect that it would jump across it. And then one question we might ask ourselves is, what will stop it? We know that fluids don't go across the bottom of a swimming pool. They would sit in the bottom of the swimming pool quite happily and wouldn't transit the liner. Why doesn't it go through the liner? Well, the liner doesn't. The entry pressures, the capillary pressure they would have to exceed to go through the liner is too high for the column in the swimming pool to be able to get across. And so that's the mechanism by which we can't get across the system. And so that's kind of the outline of what we'll talk about today. And so I'll get rid of I'll get rid of this. I want actually to go back to our syllabus and briefly say a couple of things. Am I not online? Yeah, I'm online. I will say that if you look at the course resources page, so today, I guess a couple of organizational things. One is that for those of you who are coming, don't have to do the quiz. And so there's a sign-up sheet with your name on it and a box. By column, you will have 100% for the first one. Don't get this going until halfway through the class, because I don't want to see the back of people leaving the room while I'm talking. And that's happened before. I'm sure you guys wouldn't do that. And so let's circulate that, not now, but sometime halfway through the class, and we can do that. So that's just operational things. If I'm sure it's not going to be anyone here. If you leave, then you just need to do the quiz, because you need to be exposed to the material. So the rationale of this is that you have to hear me talk about these things to be able to take it into your psyche as part of the course material. The second is that today, live will become the first assignment, due next Thursday at midnight. And rather than talk about it in class, if you look at the lecture from last year, I think 2018, you'll see some discussion in the early stages of that. But online, there's actually an overview.
The assignment is basically to do this.
Yeah. And so
the idea is there's 3 Pascal sections.
So you can look through that and educate yourself if you feel so inclined, or you can just do the assignment and it'll give you some background to what you need. But also online is something, Jihao was TA for this class last year, is also TA this year. He also produced a kind of a crib sheet for it. Yeah. January the 10th, 2018 is the date at the top. And so those are the resources that are available to you for doing the assignments, if you so wish. Or you can go and talk to Jihao. You have his office hours, which are 3 to 4, Tuesdays, Thursdays. And so those are the resources available to you. And so based on that, I won't belabor the point by going through that any further. Okay? Any questions from last time I should ask before I start off on this merry journey? Puzzled looks? No?
They do next Thursday.
Yeah, next Thursday. Today, by midnight today. Yeah, the same, and it will be a pattern, same deal each time. All right, so let's see what I've got. Whoops, don't want that. I do want that. I do want that. You've seen this stuff before, right? All right, so the plan today is that, so we'll start talking about physical hydrology, the first topic in the syllabus. And we will talk about the difference between lighter than water and denser than water non-aqueous phase liquids, the acronym for NAPLs. And we'll talk about the mechanisms by which they travel in the subsurface. The little video that we just watched is a kind of introduction to that, to be able to explain the principles as they should be. And we'll come to the conclusion that how they move through the subsurface and where they stall within the subsurface, stop, is all a function of interfacial behavior, surface tension. Same things that allow water walkers to walk on ponds, the surface tension of the liquid relative to the vapor above it, the air, are the same mechanisms by which the controls are set on transport of non-aqueous phase liquids in the subsurface. And so we'll talk about that in terms of just sitting on a substrate of glass. What happens if instead of being on a substrate of glass, they're pouring through bead packs, stacks of marbles that have pore space between them. And then we'll use some analogs that represent those behaviors that can give us very simple models to allow us to be quantitative about how this behavior evolves. And so really in this class, like any class that you may have had from me, it's all about being able to put some numbers on these phenomena that we expect to see. And so we made this point that there are these two classes of materials, L-NAPLs and D-NAPLs. Apparently the phrase L-NAPL was coined at the time of Love Canal. When is that? Late 80s? Late 70s, early 80s? When the lawyers wanted something that sounded nice. L-NAPL sounds like apple, can't be bad, can't be killing people from the carcinogenic effects of these spilled fluids. And apparently that's the origin of the term, NAPL, L-NAPL. And the behaviors of these two classes of fluids, lighter than water, and denser, is that, let me see, I can make this a bit bigger. So the idea is basically this. So you spill something on the surface, and because it wants to soak into the ground because gravity is pulling on it, it will move into the subsurface, into this porous medium. If it's moving in broadly open pore space that doesn't really have any resistance to it moving in it, then it will keep on going down. When it hits the water table, it's the same as putting gasoline on top of a swimming pool, except it's in a porous medium. But the principle is the same. If you pour gasoline, lighter than water, onto the top of a swimming pool, it'll spread out as a sheen. Pour more gasoline, it will sit just like salad dressing in a salad shaker with the lighter fluid, the oil sitting on top of the vinegar, which is water mainly, and they're separated and they're segregated based on gravity. But when it hits the water table, then what it will do is that it can potentially displace the water table. So as this goes down, this is the water table here, which there's this, well, the water table is actually this solid line here. Can you guys see that, by the way? Probably make it bigger. And so what will happen is it will get arrested by the water table because it's buoyed up by it. And you end up with this lens developing, which will look a bit like this, not very well drawn. But this will essentially be a puddle. A puddle because the bottom of the water table is now moved down and is cushioning it, sculpting it like a saucer. And the top of it because there hasn't been enough added here to be able to spill out beyond this. And so this will be a lens that will be present where basically this non-aqueous fluid, gasoline will completely fill the pore space, and it will depress slightly the water table. This material here will be a chimney that has a smear on it, mainly filled with air in the pore space, but has a smear on it. And we have to worry about two things. We made the point last time that if this stuff doesn't dissolve in water, then we don't care about it. So if it didn't dissolve in water, it would sit here in perpetuity, and so long as you don't try and suck some of the water out of here, then you don't have a problem. But if this water table has a gradient to it, I'm going to make this a bit smaller, then the gradient of the water table will look something like this. This is the change in head with a length, and we know from Darcy's law that velocity of flow is equal to hydraulic conductivity times the gradient of head, with a minus sign after to it. This is Darcy velocity, by the way. And so there should be a flow in this system that's going in this direction. So it dissolves in the water around here, which is what this stippling here is supposed to represent, and then it gets carried downstream as a plume. And the plume will go progressively further and further with time. Also, it'll vaporize, because these have gasoline. You know, if you leave it out, it'll evaporate. It'll evaporate in the subsurface. Subsurface is probably 55 centigrade, 10 degrees, 55 Fahrenheit, 10 degrees centigrade. And over time, it'll evaporate, and so it'll travel in here in the pore space, which is air-filled. And so these are the mechanisms that we're interested in looking at. We're interested in figuring out, one, what does this lens look like? What are the controls on where that is, how big it is? We're interested in what is the amount of fluid that might be kept in with this chimney. And that's the first thing that we'll try and answer in this class. And then after that, we're interested in figuring out how quickly that might travel downstream as a plume, dissolved in water, not as a free phase, and how quickly it might distribute itself in the vadose zone where it's traveling in air by diffusion. And then the third part, which really you will do, is the question, what can we do to get it out of there? And so you could imagine that we could suck stuff out of the water table, we'd remove the dissolved stuff, but we'd still have this source that was producing the dissolved plume. And if we don't get rid of the free phase, FREE phase plume, or source, if you like, then we actually don't make much of a dent in the remediation. So typically the desire would be to take this out as a source, and if we can't do that, then maybe at least stem the migration of the plume as it goes down gradient, and that might be a good strategy if you think you're going to own something for 50 years. You don't want to put the big bucks into removing the free phase, but you think you can afford to pump a bit of water and put it through activated charcoal for 50 years at a lesser cost. And so that's actually where lots of remediation projects are in this day, this choice between these two outcomes. Get rid of it for perpetuity in one fell swoop, expensive. Deal with it on an ongoing basis and just take care of the migration and stop it from causing any harm elsewhere. So LNAPLs, lighter than water, non-aqueous phase liquids. Those fluids that are denser than water will behave kind of in the same way. You can imagine that it would migrate down through here. Here's the water table that we go across. But now, just as the same as you drop something which has a density of 1,600 kilograms per cubic meter in a swimming pool full of water at 1,000 kilograms a cubic meter, it won't stop at the surface and cause a sheet. It'll go down to the bottom of the pool. And the fact that this happens to be filled with porous medium isn't significantly different. It'll still tend to that behavior. And so what it will do is it'll keep on migrating beyond the water table and the vadose zone, top of the vadose zone, the partially saturated zone, and it will stop when it hits something. And the question is, what causes it to stop? It is capillary rejection, as we'll talk about. The pores are too small for it to get in through with the surface tension. And it will cause here, this will be this puddle that will exist here, same as the puddle before. Instead of resting on the water table, it will rest on a capillary barrier. So this is a capillary barrier that's here. And again, the same constraints are for if it sits there forever, we don't care maybe. But if water is traveling across it at some velocity, then you can imagine that this stipple here represents the plume that gets carried downstream. And also this smeared chimney that's present within the unsaturated zone and the vadose zone will also be able to vaporize. Nothing much will come out, but it will come out of the ground. And it can also move as a plume of gas, a vapor plume, within the subsurface above the water table. And so that's kind of the properties that we're interested in figuring out for this particular system. We've given part of the game away in that we've said that the controls on this, well, the two controls. One is that gravity and negative buoyancy, just like me dropping this pen, is the mechanism by which it moves downwards. That's the impetus for it to go downwards. And the mechanism by which it stops is it meets a barrier. And that barrier is really controlled by typically low permeability materials, clays and shales instead of sandstones and gravels. But it's not the low permeability of them that makes the difference. It's the fact that the pores are very small, which means that the permeability is low, but the mechanism that stops it from transiting is actually the capillary behavior. And so this again is just another little cartoon that shows that behavior. For lighter than water non-aqueous fluids, phase fluids, denser than water non-aqueous phase fluids, you get these plumes developing that sequentially at times 1, 2, and 3 go progressively further and further down gradient. Or if you look at thinking of this as a single snapshot in time, then this is the lowest concentration, and these would be progressively higher concentrations as you get closer to the source. And so there are a variety of features that you can see in these non-aqueous phase liquids. And this might take a day, a week, a month, maybe a year, but not 10 years. It'll reach this equilibrium quite quickly. And the true behaviors that you see are fingering, that they don't stay in a single line, but they choose kind of erratic paths by fingering. They're kind of unpredictable. And for DNAPLs, as we've kind of suggested, they can be quite penetrative, because if you don't have this base of the swimming pool, this low permeability, high capillary entry pressure barrier, then it will just keep on going down as long as gravity can drive it. And so those are the behaviors that we'd expect to see. I think I've got some pictures somewhere. Actually, let me go back here. Look at this. Yes, this is actually, I like this picture. And so this is actually a laboratory picture of exactly that process. So it's a bead pack. These are small, they're not marbles, they're probably 1 millimeter size grains. And there's two gradations of them. Very fine grains, coarse grains at the top, fine grains at the bottom. This red stuff is a dye that's attached to one of these non-aqueous phase fluids, a DNAPL in this particular case. And you see a couple of features. The first feature is that the boundary between these two bead packs is kind of along that. They're coarse above it with big pores, and they're small below it with small pores. And you see there's a kind of an exclusion of this as it's tried to go across it. The exclusion hasn't happened everywhere because you've got breakthrough at a number of individual locations. And so the question is, what is special about these particular locations that's allowed it to form these little, we call them ganglia, plural, a ganglion singular, that has allowed this to pass through the system and to allow it to be held in this particular location? And the answer is that what it probably has done, and we'll explore this later, is probably found a pathway where some of the beads are a bit further apart, and therefore the grain, the pore throats are larger, and therefore the forces that exclude it from invading that particular pore throat are smaller, and therefore it can overcome. Gravity is enough to drive it down through it. And at some stage there's enough resistance to this that it's actually stopped and not gone any further. So I guess there's some things that we'd like to know about this for our own benefit. How do we know when this will happen? How can we calculate what gradation, for instance, it would take that would stop this? Because then we might have some confidence in looking deeper down and thinking that things are not there. How can we decide when it would go across here as these ganglions? And is there a way for us to be able to take this region here as a whole and to be able to classify it in some way that describes its behavior that is a useful engineering or scientific description? And that scientific description is what we will call saturation. And if we know the saturation of the DNAPL within that block, then if we multiply it by the volume of that block for our whole field site, we have a chance of figuring out how much we have in place and therefore how much we have to remove. So that's one question we might ask. And the question is, if we know exactly where it's migrated to, we probably also have a good feel for being able to calculate whether, for instance, if we pumped water across here, across this little block, whether we'd be able to move any of this red stuff to be able to come towards our well, beckoning it towards our well so we could recover it and take it out. Turns out that the chances of being able to move this with the gradient you applied by flowing water is probably close to 0. And so, but we should understand the reasons why that is so. And that's kind of where we're going in this. Oh, I didn't want to do that. Anyway. Okay, so that's kind of where we're going. And you can see some other pictures of these behaviors if we look at this. Not great pictures in terms of what's going on, but it makes the point of what's happening in this. If I actually, this is exactly the same. This is a zoom in on one of these things. Here you have the stuff that's traveled down through here. It's tended not to go outside through here, and presumably it's because some characteristics of this bead pack, which in all intents and purposes, you can see it's quite regular, right? Marble, 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 marble. It's not face center cubic, it's the other one. What's the other one when it's in the interstices for the individual particles? Face center cubic is grain on grain, right? When they're offset by half a diameter, then it's something else. It doesn't matter. And so that is the behavior at fine scale, which we'd probably like to be able to understand what's going on. And then we can apply this at much broader scales, where we have an aquifer that has a water table placed in it. We spill some of this fluid from the surface. It makes this chimney until it finds a little low permeability layer. That low permeability layer it ponds on top of until it flows off the side or flows through it and continues with this chimney, finds another layer that it flows off the sides of and ultimately hits the water table on this side and is present then as a plume that can be carried downstream in the water. So those are the characteristics that we're looking at. And so this is just representing the stratigraphy that at each of these locations there's a layer which is less permeable than the material above it. And the important thing is not the permeability, which we measure by hydraulic conductivity or the permeability coefficient, or permeability itself. It's the fact that the characteristics are that the grain size are smaller, and therefore the pore size is typically smaller as well. So if you look in the notes, a bunch of experiments in basically aquariums that are filled with porous media, sand and water, and spilling these fluids through them, and you get these, as we've said already, these quite irregular shapes where you get these smears that aren't completely saturating the material 100%, but that we'd like to know exactly what are the controls that give these different geometries in the subsurface. So that's our first task in trying to understand this. And so we've made the case that it's something to do with surface tension. And so let's follow that. Surface tension, you understand, can be defined in terms of two things. Surface tension is the tension that exists when you have two fluids in contact with each other. A fluid that's in contact with its vapor. And interfacial tension is when you have two fluids in contact with each other. And so interfacial tension would be if you had oil and vinegar in the same container. The tension between those is interfacial tension, defined by the two individual components. If you then physically force them to be apart, then the vinegar, which is really water, acetic acid is mainly water, would have vapor above it. Just like cavitating a fluid, you vaporize it by applying a tension that makes it into bubbles. The vapor exists above it, and the tension that you'd feel in those is actually surface tension. So if you take oil and water, you pull them apart, you have vapor of the oil above and the water below. It's interfacial tension that exists when they're in contact in this form, and it's surface tension that exists between the water and the water vapor above it in the second case. And we can define a formula that says if we want to separate them, the work that we have to do to pull them apart is equal to the surface tension of the water, the surface tension in contact with water vapor, the surface tension of the oil in contact with the vapor of the oil, minus the interfacial tension between the two fluids when they're joined. It's a definition of expression. You'll never have to use that, so fine, mark up what it is, but that's just to kind of set the stage for what we'd like to be able to figure out. So what we'd like to figure out is that we're not so interested in a sheen of gasoline sitting on top of a swimming pool, but we're usually interested in solids being present. But as a first example, we can think about how that behavior on a swimming pool acts. And so if you take a drop of gasoline and you put it, well, you can take a beaker for that matter, a drop of gasoline in a beaker, and you drop it, you could imagine that it would sit as a drop on the top of the water, but it would try and spread out. So in trying to spread out, you can imagine that originally a drop would try and sit kind of like a drop, but it wouldn't be able to manage that very well. And what it would you could probably imagine it would do is it would attempt to spread. And in that spreading, to look like this lens that we've kind of already seen, one tail end of that lens would look like this. This is the water below. This is the second liquid that we've added to the system, which is gasoline, say, because it's lighter than water. Otherwise it wouldn't float. And we have air or vapor above it. And so we can do a very simple force balance to be able to figure out whether it would sit there as a globule or whether it would spread to completely cover the surface. And that is just by looking at the interfacial forces that would exist, which are defined by these interfaces. So this is the lens. We can imagine a force that is due to the interfacial tension between the liquid and the gas above it, liquid B and gas, sigma Bg. We can look at the interfacial tension between the liquid A and liquid B, which is this. You notice it'd be slightly depressed because instead of just having atmospheric pressure acting on this boundary, it's got the self-weight of this small column. And this is this small column that's sitting here. And pulling in this direction, we have the interfacial tension between the gas and liquid A. And so if you just do a force balance where you realize that this has some angle, theta, then this is the expression that defines equilibrium. AG is pulling to the left. AB is pulling to the right, but with some included angle, which is the cosine AB. And BG is pulling to the right as well, modulated by the component which is in the horizontal direction. And so all this is saying is that these are material properties that we think we can know. These are probably parameters that we can get. But if we assume that these values are equal to 0, then each of these would be equal to 1. And if we do that, then we can just do this force balance. And it says that in a physically satisfying way. If this force pulling horizontally to your left is bigger than the combined effect of these two forces pulling to the right, then this boundary is going to move to your left. If it moves to the left, there's nothing that's going to stop it, and that's the criterion that you have to satisfy to be able to get a sheen that sits on the water. So, again, interesting stuff. We probably won't use it in this class, but kind of setting the stage. The one we are interested in is the windshield system. You have a drop of water that sits on a windshield, comes down through the air, so it's a drop of water, a bead of water that's surrounded by air around it. It's sitting on glass. Take the windshield, make it flat, and then you have the system that's shown at the bottom. And you'd expect it to look like this. The bead of water, instead of sitting as a marble, a sphere, will flatten, as you know. It will have some shape where now this lens, which looked like this before, with a liquid, and a gas, is now a liquid, a solid, and a gas. And this perhaps isn't a bad analog for what our porous medium would be if we have stuff in the subsurface. And so we can do the same calculation. Force balance, now the angle here has to be horizontal. This is the interfacial tension between the liquid and the solid. Gas in the liquid and the solid in the gas. Again, we can do the same thing of making the angle theta go to, actually we can keep this angle theta, and if we rearrange things we can figure out exactly what are the criteria for this to spread. And the criterion would be that this value of interfacial tension has to be larger than this component plus this component times cosine theta, this term here, just written out. And we could use that if we knew theta to be able to figure out whether it would spread completely across the substrate, which we'd call a wetting fluid, a fully wetting fluid, or we could use it to try and solve for this angle here if we knew the interfacial tensions and we didn't know this angle here, we could solve for that. We could do either. But again, in the limit, if we allow this angle theta to go to 0, then this term here would also go to 1. We can rearrange this term here and define that when the interfacial tension between the solid and the gas is greater than the sum of these two interfacial tensions, then it will actually form a sheen that exists on the surface, so-called fully wetting. And so that kind of sets the stage for us. We won't worry too much about this angle, but we will use the idea of exactly what this bead might look like on the surface. And the important components are that it defines what we'll refer to as wettability. And it's defined by this angle only, not these values of interfacial tension, although these values of interfacial tension contribute to that angle. And if this angle, always measured in the densest fluid, and remember fluids can be liquids or gases, so both this gas and this liquid are fluids, but only one is a liquid. So the density is measured, so the angle is measured in the most dense fluid, gas or liquid. And the convention is that if theta is less than 90 degrees, so this is 90 degrees, so if theta is less than 90 degrees in this case, we'll call it a wetting fluid. So this is so L so-called wets the solid is one terminology used. If this angle is greater than that, then I suppose if I drew this out, then the bubble would now look like this, right? This angle here would be theta. So this green is the contour of what the bubble would look like. It would be a bead that would be sitting on top of the surface, and it would have a gap underneath its edge at this particular side. This is something that's non-wetting. And so you think of these in terms of hydrophilic. It likes, this is a substrate, quartz if you like, or glass, that is hydrophilic. It loves water, and therefore it allows it to spread across it. This green one is hydrophobic. It abhors water, or sorry, the solid abhors this fluid, and therefore it's hydrophobic. And the terminology that we give these are a wetting fluid, and this is non-wetting. And you can imagine this is important. If indeed it's this surface tension at the boundary that controls the migration across it or into a pore space, then knowing whether it really wants to get to know the solid versus hates the solid, you could imagine might make some difference as to how this migration process would proceed. And so wettability is something that we understand. And you've seen this before. If you had the misfortune to take 303, you've probably understood this in the idea of capillary behavior. You take a capillary tube and you dunk this capillary tube into a liquid. And you could imagine a couple of different behaviors. If it's water and glass, glass is the same as quartz, same as sandstone. Water typically wets glass, and so it will climb up this tube as far as it can get and sit there. And so the water would climb up here to look like this, not a very good diagram. And it would have this interface angle here, which is our theta, which is this. This is just one part of this, right? This is this part here. And we'd say that the water wets the glass. The classic example for this in fluids classes is to put the capillary tube into mercury. And if you put it into mercury, then all of a sudden it looks like this. And the two characteristics are that one, the mercury level is now depressed. It's below the level. It's been kind of pushed down as you push the capillary in. And of course this part here is this part here. And so clearly these behaviors are different. The red line for a water-wet fluid or a wetting fluid and the blue line for a non-wetting fluid look completely different. And therefore you'd expect that in each of these systems, if for the same fluid you had a sandstone, which is quartz, for which water is a wetting fluid, it would behave in a particular way. And if you're pushing water into a limestone, which is a non-wetting mineral, then it would behave in a slightly different way, completely different way. And so we need to be aware of that. For the purpose of this class, typically we will take the reservoirs as being water wet, and the non-wetting fluids are either the non-aqueous fluids, petroleum. So petroleum is the non-wetting, and water is the wetting. Air is also typically the non-wetting, and water the wetting. And for NAPLs, non-aqueous phase liquids, where they're dense or light, then again, this is the non-wetting fluid, and this is the wetting. And so that's important. So that's the first thing. The take-home message from what we've talked about so far is there are two different behaviors, non-wetting behavior and wetting behavior. And so if we look at real materials, what does that physically mean for us? These are the figures that we looked at. And again, the pages of handwritten notes that we've just gone over are going to detail the things that I'll say now, but I'll say them rather than referring to those and just use the visual. So wettability is important. We said that for our systems, water is the wetting fluid. Let's assume that's the case. The oil is the non-wetting fluid. These concepts of multiple fluids in one porous medium really grew out of petroleum engineering. It predated the ideas of having DNAPLs and groundwater. And so most of the literature revolved around getting oil out of a reservoir, where oil is the non-wetting fluid and water is the wetting fluid. Obviously, they're initially in place. And so what you'd expect this to look like in terms of a water wet sand, our usual reservoir, is that the black is oil, the white is water, and the stipple are the grains. So this is a porous medium. So if you find a reservoir where you have a high proportion of oil in the pore space relative to the water, it would look something like this. It would have what we refer to as the saturation, which is the water. And if you imagine, you see these little triangles of water here, and if you think of this as a grain-grain boundary, you could imagine that at this grain boundary, if you had water just held there on its own, then the water would actually occupy this portion, which is actually the white stuff here. And the dark would be the air or the petroleum, which is outside this. So this initial saturation that we have, which is referenced here, are so-called pendular rings. And so you can imagine that as this sits, the water saturation here, there's a grain-on-grain boundary, and what there is there's a donut or a torus of this water that surrounds that contact that is underneath the grain-grain contacts as maybe a monomolecular layer that's between these grains if they're just pushed together, and also as a ring, a pendular, so-called pendular ring around it. And then outside that, the rest of this stuff is filled with the non-wetting fluid. Oil reservoir or a DNAPL contaminated site, you want to be able to replace pull out the DNAPL to use it as oil or to get rid of it out of the aquifer. So if you pump water into this system, since it's a zero-sum game, you only have a certain volume of pore space. Mass balance requires that the water that you push in has to push out something else. If it pushes out water, then there's no change. But if you push in water and it pushes out the non-aqueous fluid, then there's a change in the proportions of those two. And so in this case, as you pump in water, you see that the white areas have grown because there's now more water in the system. So you're adding H2O into the system. These pendular rings grow from their particular locations, and as a result, as a consequence of that, the blobs of oil, which are really starting to form bubbles now, solid oil bubbles, are reducing in size. And if you continue this, then you get these little individual bubbles that are now isolated. So this is what we call pendular saturation. Of water. A term not that you have to memorize, but just a part of the vocabulary. Like a pendant, something hanging there, I guess is probably the root of the word. And it's these little donuts that go around the grain-grain boundaries. And as we change this, we end up with what is referred to as funicular saturation. Must be a Latin word. Funicular saturation. And in the same as a funicular railway is a cog railway that goes up a mountainside, right? You have a train on tracks, can't get traction from running the wheels, so you have a cog that runs against a rack and pinion steering, a rack that's a serrated thing that you have a cog that drives the train up the mountain so you don't drop 4,000 feet off the side of the Eiger. Funicular means exactly that, is that to get these bubbles out, you have to physically carry them with the motion of the water. And so funicular is the advection, if you like, by requiring to carry these bubbles. And so as you get this transition, as you keep on adding water to this system, you end up changing the geometry of the saturation. And this is important. It's important, as we'll talk about it, because you can imagine that although it's difficult to see this in 3D, you can imagine that the water that surrounds the grains could be completely isolated to a single donut. And if you have a single donut and you're pushing water in here, there's no reason why that water should get into that single donut and be able to transit all the way across these multiple linked donuts, because they're not linked, get to the other side. And therefore, pushing water in from one side doesn't push water out the other side that flows through. What it has to do is it has to swell this particular donut, make it larger, until it's connected as a fluid. And until it's connected as a fluid, you'll only produce oil out of the other side of this. Once it's connected as water, you'll produce, I guess that might be worthwhile doing. So this is, here you produce only oil. Here you produce oil and water, because now it's connected all the way across here. You can get from one side to the other only in water, and you can also get from one side to the other probably still in oil. But when you get to this case here, you pump water in on this side, you only have a connected pathway in the water, and the only way that you can get these bubbles of oil out is if you can carry them by viscosity, by friction really, dragging them with friction, and that ain't going to happen. It doesn't happen. Just, I'll tell you that in advance, but we'll show it later on. And so this stuff is stuck in there. And so the bottom line is, when we talk about remediation methods, using things like pump and treat, fine. You can get out the first large saturations of the invading fluid, the non-wetting fluid, but once you get down to much lower concentrations of that, it's stuck in there. Of course, it's not a problem if it doesn't dissolve in water, but it does dissolve in water. And so that's what we have to worry about. We said before that wettability depends on the liquids, the fluids, and also the material. So water-wet sand would be a sand, and an oil-wet sand would be, for instance, a limestone sand, which is a wetting, typically wetting. And so it behaves in the opposite way. And the opposite way is that the bubbles that are held in here are the water, the wetting fluid, the non-wetting fluid. And, well, that's confusing, isn't it? You can see that just one is just the exact opposite of the other. So probably it's easier to think of being the same material, the same sand, but using different fluids. So now, if you use some fluid which is the non-wetting fluid, it will be this white bubble, and the wetting fluid will be the black pendular ring. And we've just switched their behaviors. Everything else is the same as these. We've just switched black for white. And so that would be fine if we switch the two fluids, which is the easiest way to understand this. But typically that's not the case we're interested in. We're usually interested in a fluid system. We have water and we have DNAPL. And we're interested in this rock or this rock, where one rock may be wetting and one rock may be non-wetting. Right? They're opposite. And so the discussion of this is included here. I mean, I think I've said all of these things for diagrams A, B, and C. Pendular rings, it's around the grain context. There's no continuous water phase that goes across, except for maybe a monomolecular layer on the surfaces of all the grains. If you pump water into it, then all of a sudden you increase the wetting phase because you're adding water and you're pushing out the non-wetting fluid, the oil. And so water saturation has to build until you get a continuous water phase. And at that stage, then you can pump water from upstream to downstream and oil from upstream to downstream. This condition in the middle with these two here. And then as you keep on pumping water in and displacing more of the oil, then you end up with more water saturation. And you end up with this so-called funicular saturation. So, just terminology. And so we'd like to be able to understand that process. Clearly you can imagine that the behaviors that we're talking about here that control these changes in saturations are probably quite important to us in the things that we want to do. Because it says something about how much oil is in place, how much water is in place, and how we are able to exchange one for the other. And so how do we approach that in something more than just this conceptual way? So one conceptual way might be to be able to, don't know why red's my favorite color, but if you imagine that within this porous medium, actually it might be just easier to draw a porous medium. So this is a porous medium. And these would be our stippled grains, just as in the previous case. within this porous medium, we kind of have a pore throat. And we can idealize that pore throat as maybe a tube, just like this pen. Circular in section, but a tube which goes into the pore space. And you could imagine that between all of these individual grains, we have some pore spaces that we can idealize maybe that look like this cylinder. And we could take that cylinder and we could try and look at what are the controls that either allow us or don't allow us to push fluids along this system, where we might be pushing in water and we might be pushing out oil, or it could be air. Because of course air is a fluid as well, a gas, but a fluid nonetheless. And so what are the controls on the boundary that we might have between these two different components? The green material at the top and the blue material at the bottom. So one obvious way that you've probably already seen, hopefully, is to think of it as a capillary tube. And the idea is that in a wetting fluid, what we might do is we might take a capillary tube, put it into the liquid. The two fluids are air above, or vapor above liquid water. And we know that if we do that, from what we just said, is we get some rise within this capillary tube that we're pushing in there. And we can do a very simple force balance on this. You know the constraints on this. We know that the pressure at this point has to be atmospheric. We know that because we can get to this point here without going through any other fluid, that the pressure here has to be atmospheric as well, because it's on the same horizontal boundary, right? You know that dP dH is equal to, as you go horizontally, pressures don't change. So you're going horizontally only. Happens to be that you're going down, then up, but you're really going horizontally. So the pressure is atmospheric. So what we can do is we can truncate this. And so the diagram for this, I'm looking for a space where I can draw it. So you can basically draw this column here. And this column here is basically this column here. And you can look at the force that you have to apply on this boundary to hold it up versus the weight of this, which is going to be equal to its volume times its density times gravity. That's it, right? And you know that the force around here, if this is a diameter, this is 2 pi r, or this is going to be pi times d is the circumference multiplied by the interfacial tension, which is what this acting up here is. So this is the contour of it around the circumference. This is the interfacial tension. And there's also an angle here, which would be cosine theta. So you've seen that before. And so if you put these two together, interfacial tension, circumference, angle of offset for the force that is acting in the vertical direction as opposed to the one which is inclined, then that's this term here. And the volume of this is just going to be what? It's the height, which we'll call h sub c for a reason we'll identify later, times the area, which is h sub c times pi d squared upon 4. So that's just this expression here. And so we'd be interested really in what, we don't know what hc is. That's what we might like to find out. And so we can take this expression and we can rearrange it somewhere in terms of hc. And if we do that, we end up with this expression here. And all that does is it tells us that the height rise is a function of two important parameters. The unit weight doesn't change very much, but interfacial tension will change depending on the fluids and the solids that are involved. And the diameter of the capillary, if you make it a really small capillary, it'll be a really big height rise. If you make it a really big capillary, then this will basically be zero. Take a tube this side, put it in water, you can't measure the height rise. Take a capillary tube, like a hypodermic needle, then it'll go up centimeters perhaps. And so this says something about the height rise. So this is useful to us because it kind of says something about what we're interested in. So we made the point before as to whether water can displace this other fluid that's in the system, because we're looking at these systems not in terms of the velocity at which the water is pushing out the oil, but actually whether it can get in or not. It's a binary outcome. Can it invade or can it not? And so we're not looking at velocities in this. We're looking merely as to whether it can invade. And whether it can invade is controlled by the diameter. If the diameter is too small, it can't. And so therein is basically the mechanism by which the DNAPL goes down. It hits a low permeability barrier, but the low permeability barrier is just one that has very small pore sizes. The pore sizes are the direct analog with the capillaries, and it excludes any transport across it. And it goes back to explaining this figure that we looked at earlier, which is this. It directly explains this behavior. All of a sudden, the capillaries are smaller here. You need a very big head to push it through that, more than just the unit weight of acting by gravity, and therefore it can't get across that. So that's kind of the first step, I guess, in our journey to figure out exactly what's going on in this. Okay. What happened? Did I close something? No, fine. What am I doing here? All right, so our interests in this are a fewfold. So instead of looking at height rises, what we could do is we could look at the fluid pressures and how they differ as you go across this surface. Clearly the pressure within the air and the pressure within this meniscus are different. The curvature actually attests to that. And what we can do is we can define something called capillary pressure, which describes that particular behavior. And so we define a term which is called capillary pressure. And it's the difference between the fluid pressure that exists in the non-wetting fluid relative to the wetting fluid. So in our particular case, as we look at this system here, whoops, I don't want a straight line. Not very straight either. So you could imagine that if you look at the pressure in the air, this is in our non-wetting fluid. And if we look at the pressure within our water, and if this is the water table here, I guess, then these two are not the same as each other. If the meniscus was flat, so in other words, if it's a really big diameter pipe and there was no height rise in it, and it looked basically like this, then indeed if we looked at these two pressures across that boundary, they'd be the same as each other. But because this has a curvature in it, it's reflecting the fact that surface tension is behaving to change, cause a difference in pressure between these two. It's a bit like actually a bubble, right? Inside a bubble there's a pressure that is pushing outwards, and it's resisted by the surface tension of the skin of the bubble relative to the pressure that's outside. They're different pressures, mildly different pressures. And so this is exactly the case. If you think of this here as a very big bubble, which goes up here, etc., then that's exactly the behavior we have. And so what we can do is we can define this difference in pressures called capillary pressure, and it's the difference by definition, the non-wetting fluid pressure, the gas in this particular case, minus the wetting fluid pressure, the water. And we can define this by merely dividing this by the unit weight of the water. And this term here is actually equal to H sub C, right? And so it's not so much a stretch of the imagination that this difference in pressure between atmospheric at this point, which is P non-wetting, and the height of this capillary fringe is actually this difference between these two pressures. And it's manifest as this height rise in a capillary. They're all interwoven, so the same processes. And so you can think of this capillary pressure, if we go back to our previous diagram, as the pressure that we have to apply in this relative to the pressure in the oil for it to move, to move the interface. If the pressure here is less than some threshold above this, then it won't move. If it's larger than some threshold, it will move, and it will go to a new state somehow, which we won't say anything about now, but it will go somewhere. And so the idea of capillary pressure is an important thing of what we will talk about, and it's related to this height rise. And the one thing that we should also note is that capillary pressure we expect to be proportional to the interfacial tension and inversely proportional to the diameter. The pressure you have to apply to move something is proportional to the interfacial tension. Double the interfacial tension of the fluid takes twice as much pressure to displace it, and inversely proportional to the diameter of the tube. So half the diameter of the tube, it doubles the pressure you have to apply to be able to move it because it's smaller and has more resistance. So anyway, so that's the first excursion into that. The other way that we could think about this, so we said that one way to rationalize this was to take a whole bunch of grains and to think that these grains had a pore space between them, and that this pore space we could idealize as a capillary tube of some representative diameter, and then examine this behavior. The other way that you could imagine idealizing these grains, and especially based on this idea of pendular saturation, grain on grain, a donut of water around it that's held by interfacial tension, that is this idea over here. The other way you could think about idealizing it instead of a capillary inside the space between these is to think about a grain on grain geometry where you have the pendular rings attached to them. And so the other way, instead of thinking of a capillary tube, it's a different way, it's no less valid, complementary in some respects, is to think of this geometry. And this geometry is you have two marbles, you put some water on one of the marbles and you put them together, and you see if the lower marble can be held there or not. You add some more water and you'd see that it would grow. And you can do the same kind of analysis as we just did for the capillary tube, but it's slightly different. I won't go through the analysis, but it relates, not completely surprisingly. Whoops. We made this case before that it was this curvature that defined a pressure that was different. That was different in one fluid to the other. So the pressure here versus here was different. You could also think about this geometry here as being the same deal. There's a pressure within the liquid and the pressure within the gas around it, and we'd expect them to be different. And the more severely, the smaller the radius of curvature of this, the tighter the radius of curvature, the more severe the difference in those pressures. The broader the radius of curvature, big radius means it's quite flat, the difference between these pressures would be quite small. And so you could do a similar analysis that we won't, but only to make the case that there are two curvatures here, right? In this section, there's clearly a curvature which has a radius that is this length. But also, if you look down on this with a bird's eye view looking down here, you'd look down on it and there'd be a curvature that you'd see that would be in plan view would look like this. So there'd be this curvature, which I guess would be this out here, right? around this waistline point here. And so it turns out that you can do an analysis to get what's called Laplace's equation, or Laplace-Young equation, just after its inventors. And similar to what we had before, the capillary pressure being the difference between a non-wetting and a wetting pressure, then you end up being, yeah, thanks, you can send that around. Thank you, whoever remembered that. Is you end up with two different radii. One for this radius here. Good luck if you can read that. It's so small, but your names are actually on there. Everyone's, and you got 100% for Tuesday, by the way. That you have two radii, and to some degree it gives you a capillary pressure, which again, just like before, is proportional to interfacial tension and inversely proportional not to the diameter of the pore, but to the curvature of the meniscus. And so this is radius in this particular case, but it ends up being the same behavior. And so those are useful in understanding the behaviors that we might get in real rocks. This perhaps, they both have two different attributes, I suppose. This to me seems quite intuitive, that this behavior is a capillary tube which represents a pore, but what it gives you only is a single value of a pressure difference when things will start to move. So you get one value. And so that's useful, but that's one perspective. What is indefinite in this is that you can do this analysis for a very small amount of water, which would give you a meniscus that might look like these red lines that are on there. Or you can increase the amount of water, and it will give you a different curvature. Or increase it even further for a bigger curvature, or even more to give you a really big curvature. So what's not defined here is what the amount of water present within the system is. So the other one doesn't care the amount of water. It gives you a difference in pressure, a single value when it will move. This will give you a whole series of different capillary pressures depending on how much liquid is in the system. So there are different analyses, but they're actually quite complementary, because what we'd like to know is exactly this behavior that we have when we look at these systems, in that as we examine this behavior, you could imagine that if you take this block that includes this, it depends on what's called your REV, your representative elemental volume. If you take an REV that's here, it would be 100% filled with red fluid. If you take an REV which is here, maybe it's 25% filled with red fluid, maybe 10%, and 90% filled with water. And so we'd like to know what these pressures are that we have to overcome to be able to invade this porous medium at different saturations, different measures of filling the pore space with a particular fluid, the red fluid, which is what we're interested in. And so I guess the bottom line is that both of those geometries that we looked at are a little bit complementary. They're idealized, but they're both complementary in being able to describe our system. And the end point that we'd like to look at would be one in which we don't just have a single capillary tube, but we have a whole bundle of them that might represent all these pores within the parallel pore spaces that we have, and that represent the porous medium. And so if you had all these different diameter pore-sized capillary tubes, you could imagine arranging them in two different specific ways. So you have some big tubes, you have some small tubes. They represent that geometry we had before, in that they represent either the big tubes in the big granulated medium, or small tubes representing the pore space in the small one. But we could imagine to group them in two very distinct ways. We could take them and arrange them, if you take a pipe and you have a wide tube, a narrow tube, wide tube, narrow tube, like this on the left-hand side. Or you could arrange them instead of being in series, you arrange them in parallel. Big tube, small tube. And if you take those and you rotate them and imagine them in our geometry where you drop these non-aqueous fluids through them, then from what we've just said, I'm going to keep them horizontal. Whoops. I guess I can. I don't know if I can actually in this. R rotates. No, it doesn't want to do it. No, don't need it. Hopefully the microphone's already on. Otherwise, this isn't very good at all. If you imagine this, because the stuff will get hung up on the narrow diameter one, it'll stop, and then it won't have the chance to actually reach the next one as it goes downstream. Whereas if it's arranged like this, it'll just scoot happily across here, end up keeping on going down to the center of the Earth, and will get hung up in the other ones, but fundamentally the behavior in these two different systems will be completely different. This will stop it migrating, this will allow it to migrate. And of course, if you look at real porous media, you could imagine that it's neither this nor this, but it's some combination of them, partly in series, partly in parallel. And the complexity of that is what gives you these little ganglion behaviors that we saw earlier. So that's kind of the problem that we'd like to be able to address. The final thing that relates to this is that if you imagine that it matters whether you have pore space which is in series or in parallel, if you have some big tubes that exist in parallel, that's a real hazard, as you can imagine, right? Drop something in, it's gone. It's not stopping for anything. And so the one analog that exists to that in rocks and soils are fractures. So you drive down the Mount Nittany bypass, you see these lovely limestone outcrops. There are bedding planes and there are fractures. And it's these fractures that you could imagine would attempt to behave just like this. And so if we want to look at the most vulnerable features in the reservoir, or the aquifer, I suppose, since we're talking about a groundwater class, then we could do exactly the same analysis that we applied for a capillary tube to represent a capillary fracture. And all that differs is something about the geometry of it. And that the geometry is that instead of a tube being dunked into liquid, it's two parallel plates with a gap between them being dunked in. If the plates are quite close together, you'd expect this capillary rise to occur between them. The capillary rise is driven in a wetting fluid or a non-wetting fluid, right? This would be a non-wetting fluid. But the capillary rise is driven by the interfacial tension along here, and we can do the same analysis. Atmospheric pressure here, cut off this height, and this becomes a volume that is actually a prism, not a prison, but a prism. Johnny English, right? What's that guy's name? Patrice Sauvage. I will turn your island into a prison. Never seen that? Yeah. He's talking about Britain as well, UK. So volume is here. So the width, the length of this, the aperture between them, which is B, and the height rise is the volume. This is the unit weight, which is rho g. And two sides of the fracture, the length of the fracture here, and the interfacial tension multiplied by probably 1, but something that's slightly different from that. And so if you rearrange this to be able to solve for this, actually you end up with a very similar relationship, which gives you a height rise which is proportional to the interfacial tension and inversely proportional, not to the diameter or the radius, but the width. Smaller the width, more it goes up. Wider the width, no resistance to flow. And so the significance of this height rise is if there's no height rise when you put this thing in, it means there's no resistance to being able to push it in because it can go very easily. And so that's our interest in all of this. And so that's kind of where we're going with this. I didn't. When do we stop? Well, we stop now. Okay, well, I will stop now. I got pretty much where I wanted to go. So what we'll do next time is that we made this case before that we have these different geometries. So we'll talk about how does this impact real geological medium. That's what we're talking about.